students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as thermodynamics. Let's see certain numericals. Please take down the numericals, people. Please take down numericals. Calculate the work done. Calculate the work done in liter atmosphere. Calculate the work done in liter atmosphere, joules. Calculate the work done in liter atmosphere, joules, ergs, and calories during the expansion of a gas. During the expansion of a gas. During the expansion of a gas from 10 liters to 20 liters. During the expansion of a gas from 10 liters to 20 liters against a constant external pressure, against a constant external pressure, against a constant external pressure of 1520 mm of mercury. 1520 mm of mercury. Now guys, they've given you the volume in terms of liters. In order to convert it into meter cube, you multiply by 10 raised to minus 3. Moreover, the pressure is given to you in millimeters of mercury. First thing I need to do is convert this into atmosphere. How do I convert this into atmosphere? To convert it into atmosphere, you divide this by 760. So this is 2 atmosphere. So the pressure is either 1520 mm of mercury, or it is also equal to 2 atmosphere. Now if I have to convert this into newtons, how do I convert this into Newton? The conversion factor is 1.013 into 10 raised to 5 newtons per meter square. Right? So now I have pressure in all the 3 units, in mm, in atmosphere, and in newtons per meter square. Now they've asked me to find out the work. Work is pressure into change in volume. Work is pressure into change in volume, right? Now first of all, first part of the question, in liter atmosphere, they've asked you to find out the work in liter atmosphere. So work will be pressure. Pressure in liters, in atmosphere is 2, and in liters, so that will be 20 minus 10. So 2 into 10, that is 20 liter atmosphere. That is the work done in liter atmosphere. Fine. Next, they've asked you to find out in joules. They've asked you to find out the work done in joules. So work is pressure. Now pressure in newtons, when you want it in joules, you'll have to take the units of pressure in newtons. So 2 into 1.013 into 10 raised to 5, and let's see this volume. The volume is going to be still in the volume will be in meter cube. So this will be nothing but 20 minus 10 into 10 raised to minus 3. So when you multiply this, you will get this answer as 2.026 into 10 raised to 3 joules. That's how you find out the work done in joules. Next, they will ask you to find out the work done in ergs. Now we know that 1 joule is 10 raised to 7 ergs. So if I want to convert from joules to ergs, I have to multiply by 10 raised to 7. So in that case, work will be 2.026 into 10 raised to 3 into 10 raised to 7 ergs. I'm multiplying by 10 raised to 7 to convert it from joules to ergs. So in that case, this will be nothing but 2.026 into 10 raised to 10 ergs. Next, they will also ask you to find out the work done in calories. Now we know that 1 calorie is 4.18 joules. I know the work done in joules, right? So I want to convert it into calories. So work will be 2.026 into 10 raised to 3 divided by 4.184 calories. This is how you convert from joules to calorie. This is going to be nothing but 484.2 calories, right? So thus I have shown you how to calculate work in all the different units, in liter atmosphere, in joules, in ergs and in calories. Next, take on next one please. Calculate the work done. Calculate the work done in liter atmosphere. Calculate the work done in liter atmosphere and in joules. Calculate the work done in liter atmosphere and in joules when 1 mole of a gas expands, when 1 mole of a gas expands against a constant external pressure, when 1 mole of a gas expands against a constant external pressure of 2 atmosphere from 1 liter to 10 liters. Expands against a constant external pressure of 2 atmosphere from 1 liter to 10 liter. Now they've asked you to find out the work done in liter atmosphere. They've already given you the pressure and volume in terms of liter and atmosphere. So I can say work is PV2 minus V1. So work pressure is 2, volume is 10 minus 1. So 2 into 9, that is 18 liter atmosphere. That is the work done in liter atmosphere. Next thing, they've also asked you to find out the work done in joule. Right? Now first of all, they've asked you to find out the work done in joules. Now we know that this was the first part of the question. Second, let's see another conversion factor. We know that 1 liter atmosphere is nothing but 24.22 calories. 1 liter atmosphere, the conversion factor is 1 liter atmosphere is 24.22 calories. So I can now convert this. This is nothing but 18 into 24.22 calories, right? When I multiply this will be nothing but 435.96 calories. But they haven't asked me the work done in calories. They've asked me the work done in joules. We know that 1 calorie is 4.184 joules. I have it in calories. I have the work done in calories. I can convert it into joules. So work is nothing but 435.9 into 4.184. When you multiply this is going to be 1824 joules. Either I could have done it this way, or I could have done it the first sum method, where I could have done the work done directly in joules, convert this into newtons, that is convert the pressure into newtons and convert the volume into meter cube. I would have directly got the answer in terms of joules. That was one method. I could have done the sum by that method also, but I wanted to show you the conversion factor. That's the reason why I showed it to you by a different method. Right? Take the next sum please. Just in case if you are not comfortable with this, you can still do the sum that by the method I have shown you in the first sum. Right? Take the next sum please. An ideal gas is compressed. An ideal gas is compressed. An ideal gas is compressed from 25 liters to a certain volume. From 25 liters to a certain volume by doing a work of 1013 joules, minus 1013 joules, by doing a work of minus 1013 joules against an external pressure of 1.013 into 10 raised to 5 newtons per meter square. Find the volume, final volume of the gas. Find the final volume of gas. Find the final volume of gas. Now guys, since the work done is given to you in joules, that means my volume should be in meter cube. To convert this will be 25 into 10 raised to minus 3 meter cube. Meter cube, right? I can say work is P V2 minus V1. P 1.013 into 10 raised to 5. V2 minus V1, that's 25 into 10 raised to minus 3. Work done is given to you as minus 1013 joules. Right? Now, in that case, I can therefore say that V2 minus 25 into 10 raised to minus 3 is equal to negative 1013 upon 1.013 into 10 raised to 5. Right? Now, this could be written as V2 minus 0.025 is nothing but negative 0.01. Right, when you divide this, you will get this answer as 0.01. Take this term on the other side, so I get V2 is nothing but negative 0.01 plus 0.025. Right, so in which case you will get V2 is equal to 0.1015 meter cube. Right, that is going to be the final volume of the gas. Next, take on next one please. Take down next one please. An ideal gas is compressed. An ideal gas is compressed. An ideal gas is compressed from 20 liters. An ideal gas is compressed from 20 liters to 5 liters. The work done is minus 8000 joules. Calculate the external pressure required. Calculate the external pressure required. Calculate the external pressure required. Now guys, since the work is in joule, that means I have to have the volume in meter cube. This is going to be 20 into 10 raised to minus 3 meter cube, and this is going to be 5 into 10 raised to minus 3 meter cube. I can say work is P V2 minus V1. So minus 8000 is equal to P V2, 20 minus 5 into 10 raised to minus 3. I have taken 10 raised to minus 3 common. So I'll get minus 8000 divided by 15 into 10 raised to minus 3 is equal to P. So in which case you will get this answer as V2 minus V1. Guys, this should be 5 minus 20. So in that case this is going to be minus 15. So minus minus gets cancelled. When you divide this, you should get this answer as 5.33 into 10 raised to 3 newtons per meter square. That would be the pressure required, 10 raised to 5 newtons per meter square. That would be the pressure required to compress the gas. Fine, do we get this thing here? Next, take on next one please. Calculate the initial volume. Calculate the initial volume in decimeter cube if the work done is 10 joules, the final volume is 20 decimeter cube. The final volume is 20 decimeter cube against a constant external pressure against a constant external pressure of 100 into 10 raised to 2 pascals. Of 100 into 10 raised to 2 pascals. Now decimeter cube, I convert this into meter cube. How do I convert it into meter cube? By multiplying it by 10 raised to minus 3. Right? Pascals is nothing but newtons per meter square. So 10 raised to 2 newtons per meter square. Work is in joule, volume is in meter cube, and pressure is in newtons per meter square. So I can say work is P V2 minus V1. Work 10 is equal to P 100 into 10 raised to 2 V2 20 into 10 raised to minus 3 minus V1. Right? So in that case you will get this as 10 upon 100 into 10 raised to 2 is going to be equal to 0.020 minus V1. Right? So in that case you will get this as V. So 0.001 is equal to 0.02 minus V1. So I can say V1 is equal to 0.02 minus 0.001. So V1 will be equal to, when you subtract this is 0.019 meter cube. Once I have this answer in meter cube, I can convert this into decimeter cube. This can be written as V1 1, 2, 3 19 into 10 raised to minus 3 meter cube. I want to convert it into decimeter cube. So multiply by 10 raised to 3. So V1 will be 19 decimeter cube. So the initial volume is 19 decimeter cube. Now, let us understand the concept of maximum work. Let us try to understand the concept of maximum work. Now, maximum work is always obtained in an isothermal reversible expansion. Right? I can say that maximum quantity of work is obtained, why I'll just show you, obtained during reversible and isothermal expansion. Of ideal gas. Now, what do you understand by maximum work? Now, I'll explain to you what are the characteristics of a reversible reaction. A reversible reaction or a reversible process takes place in large number of small steps. Right? We have done this. Therefore, work done is a path function, and hence it depends upon the path followed by the process. Greater the number of steps, more is the work done. Right? In reversible process, the difference between the acting force and the opposing force is infinitely small. This was also one of the characteristics of reversible process. Right? And hence maximum amount of work is obtained. So why is maximum amount of work obtained in a reversible and isothermal process? Because reversible process takes place in large number of small steps. Takes place in large number of small steps. Reversible process takes place in large number of small steps. Work done is a path function, meaning it depends upon the path followed by the process. It depends on the path followed by the process. Right? So as such, I can say that the greater the number of steps, more will be the quantity of work done. I can say that greater the number of steps, larger is the quantity of work done. Right? Now, in reversible process, the difference between the acting force and the opposing force is infinitely small, and in reversible process, the difference between the acting force and opposing force is infinitely small. Hence, I can calculate work by first law of thermodynamics. I can say by first law of thermodynamics, by first law of thermodynamics, if I apply first law of thermodynamics, I can say Q is equal to delta E plus W. That's my first law of thermodynamics, right? Now, for an isothermal process, we know that delta T is equal to 0. For an isothermal process, we know that the change in temperature is 0. If the change in temperature is 0, that means I can therefore say that the change in internal energy of the system will be 0. If the change in temperature is 0, that means the change in internal energy of the system will be 0. If the change in internal energy is 0, then I can say therefore Q will be equal to W. That means the entire heat supplied to the system is going to be used to do external work for the system. And that is the reason why you have maximum work done in an isothermal reversible process. Fine, do you get this in here? I can say therefore the heat absorbed by the system is utilized to perform work by the system. So there are two reasons why you have concept of maximum work. A, during reversible process, you have reversible process taking place in large number of small steps, and work done depends upon the number of steps. Since the number of steps are maximum in a reversible process, therefore work done will be maximum. Work is done in each step. Moreover, in an isothermal process, the change in temperature is 0, hence the change in internal energy is 0. Therefore, the heat supplied to the system is used to do external work. Hence, maximum work is done in an isothermal reversible process. Fine, do we get this thing clear? Now, let us derive an expression. Now that we know when is maximum work done, let us derive an expression for maximum work done. Work done during reversible and isothermal process. What is the work done during reversible and isothermal process, right? Let's consider a cylinder fitted with a weightless, frictionless piston. Let us assume the cylinder is filled with n number of moles of gas, right? This is your piston. Cylinder, you have n number of moles of ideal gas. Right? Now let's assume that the pressure exerted by these n number of moles of ideal gas is P. With pressure P. Let us assume that P is the pressure exerted by n number of moles of ideal gas. Right? Now, let's just write this much down. Let's write the assumptions down. Consider n moles of ideal gas. Let's consider n moles of ideal gas enclosed in a cylinder fitted with weightless, frictionless piston. Right? Pressure of the gas molecules is P, which is slightly greater. Pressure of gas molecules, let's assume, is P, which is slightly greater than the external pressure. Let's assume that the external pressure is, say, dP. Right? The pressure exerted by the gas on the piston is P. The pressure exerted by the piston on the gas is dP. Hence, I can say that the external pressure becomes P minus dP. The total pressure that is going to be exerted on the piston, the external pressure becomes this much on the piston. This is the pressure that is going to be exerted on the piston. The internal pressure, the pressure exerted by the gas on the piston is P. The external pressure is dP. So the net force or the net pressure exerted on the piston is going to be P minus dP. Now, we know that work done is a product of pressure and change in volume, but work done is a product of pressure and change in volume. Therefore, I can say that work done is equal to external pressure into volume. We have done this derivation. So I can therefore say that work done is P minus dP, that is the pressure that is exerted on the piston into volume. Let's assume that the volume due to this changes by a small amount dV. Let's assume this is the change in volume dV. dV is the change in volume, right? Therefore, if the volume changes by a small amount, that means there will be only a small amount of work done. Therefore, my work done will be dW. Hence, I can say dW is equal to P minus dP into dV. Open the brackets and simplify. dW is P dV minus dP into dV, right? But dP and dV are extremely small terms. Since they are extremely small terms, their product will approximately be equal to 0. When you multiply extremely small terms, their product will be equal to 0. Therefore, I can say that the work done is P dV. Right? Do we get this thing here? Now, if this is the work done in moving the piston by a small volume dV, then in that case, what will be the total work done? The total work done. The total work done when the volume changes. When the volume changes from V1 to V2. Let's assume that the volume changes from V1 to V2. Then the total work done, W, can be given as integral of work done in one process when the volume changes from V1 to V2 But dW we have calculated is nothing but P dV. This is nothing but integral of V1 to V2 P dV. Right? Now, for an ideal gas, by Gass's law, I can say that PV is equal to nRT. Gass's law says that PV is equal to nRT. Therefore, I can say P is nRT upon V. Substitute this value of P in the equation of work. So I can say work is integral of V1 to V2. P can be written as nRT upon V dV. nRT is constant, comes outside the integral. So in that case, this is going to be nothing but nRT integral of V1 to V2 1 upon V dV. Right? So in that case, I can therefore say that if I integrate this, integral of 1 upon V is nothing but log V. This can be written as the total work done is nRT log of V when the limits are V1 to V2 to the base E. Right? Integral of 1 upon V is nothing but log V. Now, W is equal to nRT, definite integrals. Substitute the value of V with upper limit and then subtract it with lower limit. It is upper limit minus lower limit. So this is log of V to the base E minus log of V1 to the base E. Right? But log A minus log B is nothing but log A upon B. So W is equal to nRT log V2 upon V1 to the base E. To convert from base E to base 10, you have to multiply by 2.303 conversion factor. Therefore, W is equal to 2.303 nRT log of V2 upon V1 to the base 10. Right? Now, if I apply Boyle's law to this, Boyle's law states that at constant temperature, PV is constant, that means P1 V1 is equal to P2 V2. Boyle's law states that P1 V1 is equal to P2 V2. Therefore, I can say that P1 upon P2 is V2 upon V1. Substitute this. Therefore, I can say that work done is 2.303 nRT log of P1 upon P2 to the base 10. Now this work which is going to be done is going to be maximum work done because it is done in a reversible and isothermal process. So this work is going to be my W max. So W max is either 2.303 nRT log of P1 by P2 to the base 10 or W max is equal to 2.303 nRT log of V2 upon V1 to the base 10. That's how you find out the maximum work done in a process. Right? Do you get this in here? The maximum work done in a process. Right? Now, once you have this, let's see numericals based on this, guys. Let's try to see numericals based on this. Take down the numerical, please. Calculate the work done. Calculate the work done. Calculate the work done when 1 mole. Calculate the work done when 1 mole of an ideal gas is compressed. When 1 mole of an ideal gas is compressed isothermally and reversibly. Is compressed isothermally and reversibly from 2.02 into 10 raised to 5 pascals to 20.2 into 10 raised to 5 pascals. Right. Calculate the work done when 1 mole of an ideal gas is compressed isothermally and reversibly, from 2.02 into 10 raised to 5 pascals to 20.2 into 10 raised to 5 pascals at 300 Kelvin, when R is 8.314 joules per Kelvin per mole. Now, since the process is done isothermally and reversibly, the work done will be maximum work. Therefore, I can say that W max is equal to 2.303 nRT log of P1 upon P2 to the base 10. So this is going to be equal to 2.303 N, 1 mole of gas, R 8.314, temperature already given to you in Kelvin scale, log of P1 upon P2. So I'll write this here, into log of P1 2.02 into 10 raised to 5 divided by 20.2 into 10 raised to 5 to the base 10. Right? So when you divide this is going to be nothing but P1 upon P2. Okay, let's multiply this. When you multiply this, first thing, in order to see 10 raised to 5, 10 raised to 5 will get cancelled. In order to reciprocate this, I will have to take minus sign. In order to reciprocate this, I will take a minus sign. So this will be minus. Why am I taking minus sign? I'll just show you once again. 2.303 into 8.314 into 300 into log of, instead of writing 2.02 upon 20.2, I'm going to write 20.2 upon 2.02 to the base 10. Advantage, I'll get the value as log 10. 20.2 divided by 2.02 will give you log 10. So this is negative 2.303 into 8.314 into 300 into log 10 to the base 10. Log 10 to the base 10 we know is 1. Now you have simple multiplication that will give you minus 5,744 joules. That is the maximum work that is going to be done. Fine. Take down next sum please. (6.6 into 10 raised to minus 2 kgs). 6.6 into 10 raised to minus 2 kgs of carbon dioxide is compressed to 2.5 into 10 raised to 5 newtons per meter square pressure is compressed by 2.5 into 10 raised to 5 newtons per meter square is compressed by so much pressure isothermally and reversibly at 300 Kelvin. Isothermally and reversibly at 300 Kelvin. The work done in the process is 1907.9 joules. calculate the initial pressure. Calculate the initial pressure if the atomic weight of carbon, if the atomic weight of carbon is 12, oxygen is 16, and R is 8.314 joules per Kelvin per mole. Okay, let's see this. I can say that first, let me find out the number of moles. First, what will be the molecular weight of carbon dioxide? Molecular weight of carbon dioxide is 12 plus 16 into 2, 12 plus 32, 44. 1 carbon and 2 oxygen, therefore that's how 44. Once you have this, then you can say that number of moles is nothing but weight upon molecular weight. Number of moles is equal to weight upon molecular weight. Weight is given to you as 6.6 into 10 raised to minus 2. Molecular weight is 44. It is 44 grams. To convert it into kilograms, you have to multiply by 10 raised to minus 3. Right? When you multiply this, you will get this, or when you solve this, you will get this answer as 1.5. So number of moles of gas that I am using is 1.5. Now, once I have this, since the work is done isothermally and reversibly, therefore the work done will be maximum work. Now, concept of maximum work, W max is 2.303 nRT log to the base 10. They have given you P1 upon P2. Right? Now, once I have this, let's substitute. Work done is negative 1907.9 is equal to 2.303, Nu found out is 1.5, R is 8.314 into T. They've given you is 300 log P1 upon P2 to the base 10. Take everything on the other side, so I'll get negative 1907.9 upon 2.303 into 1.5 into 8.314 into 300 is log to the base 10 P1 upon P2. Right? How do I get rid of the negative sign? To get rid of the negative sign, reciprocate. If I reciprocate, this will become 1907.9 divided by 2.303 into 1.5 into 8.314 into 300 is equal to log P2 upon P1 to the base 10. Now once I solve that, I should get the answer for that as 0.2214 is log of P2 by P1 to the base 10. Take log on the other side. If I take log on the other side, it becomes anti-log. So anti-log of 0.2214 is P2 upon P1. If I take anti-log of this, I'll get this answer as 0.6006. 0.6006 is P2 upon P1. They've given me the value of P2. They've asked me to find out the value of P1. So I can say P1 is P2. P2 is given to you as 2.5 into 10 raised to 5 upon 0.6006. Right? When you divide this, you will get this answer as 1.5015 into 10 raised to 5 newtons per meter square. That is the initial pressure. Next, take down next sum please. Take down next sum please. Calculate the maximum work done. Calculate the maximum work done calculate the maximum work done when 2 moles of a gas is expanded from when 2 moles of a gas is expanded from 10 meter cube to 20 meter cube at 300 Kelvin, from 10 meter cube to 20 meter cube at 300 Kelvin if R is 8.314 joules per Kelvin per mole. Right? They have directly given it to you in the sum that you have to calculate maximum work. So apply maximum work formula. Maximum work is 2.303 nRT log to the base 10 V2 upon V1. Right? Let's substitute the values. So in that case, this will be 2.303. N is 2, R 8.314 into T. T is 300 log V2 20 upon 10 to the base 10. Right? So this is going to be nothing but 0 gets cancelled. So this is log 2 to the base 10. So in that case, this will be 2.303 into 2 into 8.314 into 300 log 2 is 0.3010. Right? Multiply this. When you multiply this straightforward, you will get the answer as 3458 joules. That is the maximum work done. Next, take out next one, please. Calculate the work done. Calculate the work done when calculate the work done when 2.2 into 10 raised to minus 2 kgs. When 2.2 into 10 raised to minus 2 kgs of carbon dioxide is compressed. When 2.2 into 10 raised to minus 2 kgs of carbon dioxide is compressed at 300 Kelvin, isothermally and reversibly till the pressure is doubled. Till the pressure is doubled. Till the pressure is doubled. Right? That means final pressure is twice the initial pressure. Now I can say W max. They've said isothermally and reversibly. That means it has to be W max. W max is 2.303. Okay. Wait, they haven't given you N. They haven't given you N. So first thing you need to find out N. We know that carbon atomic weight is 12, oxygen atomic weight is 16. So first thing you find out is molecular weight of carbon dioxide. Molecular weight of carbon dioxide will be 12 for carbon, 16 for oxygen. There are 2 atoms of oxygen, therefore 16 into 2. So 12 plus 32, that is 44. Then you find out number of moles. Number of moles is weight of gas divided by molecular weight of gas. Right, weight of gas they've given you is 2.2 into 10 raised to minus 2. Molecular weight is 44 grams. To convert it into kilograms, you multiply by 10 raised to minus 3. So in that case, you will get N is 0.5. Once you get the value of N, you can find out W max. W max is 2.303 nRT log to the base 10. They've given you P1 and P2. So in that case, this will be nothing but P1 upon P2. Right, so this will be 2.303 and you found out is 0.5. R you should know by heart, 8.314 if it is not given to you in the sum. T is 300 into log P1 as it is. P2 can be written as twice P1 to the base 10. Now this can be written as P1 and P1 gets cancelled. I have 2 in the denominator. To bring 2 in the numerator, if I have to reciprocate, I have to take negative sign. So this will be minus 2.303 into 0.5 into 8.314 into 300 into log 2 to the base 10. But we know the value of log 2 to the base 10 as 0.3010. So this is negative 2.303 into 0.5 into 8.314 into 300 into 0.3010. When you multiply this, you will get this answer as negative 864.49 joules. Right? Take down next one, please. Carbon monoxide is allowed to expand isothermally and reversibly. Carbon monoxide is allowed to expand isothermally and reversibly at 300 Kelvin from 10 meter cube to 20 meter cube, from 10 meter cube to 20 meter cube, and the work obtained is 4.754 kilojoules. The work obtained is 4.754 kilojoules. Calculate the number of moles of carbon monoxide. Calculate the number of moles of carbon monoxide if R is 8.314 joules per Kelvin inverse per mole inverse. Now since the work was done isothermally and reversibly, that means the work done has to be maximum work. So I can use W max formula. W max is 2.303 nRT log to the base 10 V2 upon V1. Right? W max is given to you as 4.754 into 10 raised to 3 is 2.303. N is not given to me. R is 8.314 into T 300 log V2 upon V1 20 upon 10 to the base 10 log 2 0.3010. So therefore I can say that 4.754 into 10 raised to 3 upon 2.303 into 8.314 into 300 into 0.3010 is going to be N. When you solve this, you will get the value of N as 2.7495. Next, take down next one please. Take down next one please. 5 moles of an ideal gas. 5 moles of an ideal gas. 5 moles of an ideal gas is allowed to expand. 5 moles of an ideal gas is allowed to expand isothermally and reversibly. 5 moles of an ideal gas is allowed to expand isothermally and reversibly at 298 Kelvin from 0.02 meter cube to 0.1 meter cube. Calculate the maximum work done. Calculate the maximum work done if R is 8.314 joules. If R is 8.314 joules. Simple, straightforward sum. Everything is given to you. they've given you that number of moles, the opening paragraph. 5 moles of a gas. So number of moles of a gas is also given to you. N is given to you. Straightforward, you can apply the formula and get the answer. So you will get W max is equal to 2.303 nRT log to the base 10 V2 upon V1. I'm not showing you the solving of this. You should be able to solve this and get the answer. The answer for this should be, you should get this answer as 19.94 into 10 raised to 3 joules. Next, take on next one please. Calculate the amount of work done. Calculate the amount of work done. Calculate the amount of work done during reversible. Calculate the amount of work done during reversible and isothermal expansion. During reversible and isothermal expansion of of 64 grams of oxygen from 2 decimeter cube to 20 decimeter cube at 302 Kelvin. At 302 Kelvin, if R is 8.314 joules per Kelvin per mole. Now oxygen, first of all let's find out N. N is nothing but weight of gas upon molecular weight of gas. So N is going to be weight of gas is given to you as 64 grams. We know that atomic weight of oxygen is 16, therefore molecular weight of oxygen is going to be 32. It's all in terms of grams, so I don't need to multiply by 10 raised to minus 3. So number of moles is going to be 2. They've asked you to find out the maximum work done. So W max is equal to 2.303 nRT log to the base 10 V2 upon V1. All the values are given to me. All I need to do is just substitute and get the answer. You should get the answer for this as 11,564.87 joules. Right? Okay, we'll stop this here for the day. Thank you very much.